Let's take a look now at example number 2. Can I compute the surface integral given here, the double integral over sigma of z squared ds, where the surface sigma is now the unit sphere. So it's given by this x squared plus y squared plus z squared equals 1. Okay, well, as we saw in the previous example, one of the first things that I would need to be able to do is to parameterize my surface. Once the parameterization is done, setting up the integral should actually be fairly simplistic. So how am I going to go about doing this? Well, as the hint suggests here, if I'm working with a sphere and I want to parameterize it, an easy way to maybe do that would be to make use of spherical coordinates. So recall that in spherical coordinates, it was the case that my x variable was always equal to rho times sine of phi times cosine of theta. Y was equal to rho times sine of phi sine of theta. And z was always equal to rho times the cosine of phi. Okay. Specifically here, if I'm dealing with a sphere, my bounds on these values would kind of be as follows. Well, I guess rho doesn't really have a bound. If I'm dealing with specifically the unit sphere, that is the outer edge, nothing on the inside, rho would always have to here be 1. I could say that phi would have to exist between 0 and pi, remember rotating from looking all the way up and rotating until I'm looking all the way down. And it then should also be the case that theta has to exist between 0 and 2 pi, so that way I can rotate all the way around 360 degrees to see the entire sphere. So I can actually go ahead and use these precise formulas then to create a parameterization. So I'll say let my r of uv, or in this case, I'll actually go ahead and do an r of phi theta, just for the sake of simplicity. I can see that that's going to have an x formula given by sine phi cosine theta, a y formula of sine phi sine theta, and finally a z formula given by just cosine phi. Okay, now you can see here all I've done is I've just replaced each of the above formulas for x, y, and z in my parameterization. I've used rho as a 1 the entire time. And instead of switching over to be in terms of u's and v's, which I absolutely could do, I'm just going to leave it in terms of the original variables. The last thing that I'll add here to my parameterization is just the bounds on my various variables here. Again, we know phi goes from 0 to pi, and theta goes from 0 to 2 pi. Okay, so now I'm ready to go ahead and actually start setting up the integral. As we saw in the last example, I'm going to need to start finding the partial derivatives for my vector function. So I'll need to go here and actually start to compute my r partialed with respect to phi crossed with r partialed with respect to theta. Now I would actually ask that you go ahead and try to pause the video here, see if you can work through what this cross product would look like. Attempt to find its norm and see if you can take it from here to actually setting up what this full integral would actually look like. And when you're ready to watch me work through the rest of the solution, you can unpause. Okay, so here's what I would have done in order to compute this integral. I can see here I'm going to set up again my cross product. So my partial derivative here is going to look like, let's see, cosine phi, cosine theta, and then cosine phi sine theta, and negative sine phi. I have my I, J, K. When I do my partials with respect to theta, let's see, I'm going to get sine phi sine theta. This is going to be negative though, so I'll toss that out front. Similarly over here, I'm going to get something that is negative. Oh wait, sorry, this one is not negative. I end up here with a cosine of theta. Okay, so when I actually go ahead and compute this all the way out, and I set up this cross product here, let's see what I come up with. For my first component, I'm going to end up with a sine squared phi times my cosine of theta. For my middle component, I can see that I'm going to get 0 when I multiply these cosines to the 0, and then I subtract what's happening here. So it looks like I'm going to get a minus sine squared of phi times sine theta. But don't forget, I always multiply this middle component by an extra negative, so that becomes plus. And then finally, for the end, it looks like I'm going to have, oof, this looks messy. I have a sine phi, cosine phi, and then a cosine squared of theta, minus, and then over here, I'm going to get a sine, looks like this is going to end up being a plus because I'm subtracting a negative. So I have a sine phi, cosine phi, sine squared of theta. Okay, so I got a really big messy cross product here, but actually a couple things simplified down pretty nicely. There's not too much that I can do here at the beginning in my first component, and there's not too much that can be done in the second component. However, if I look at this third component, I'll note that there is actually going to be a sine phi, cosine phi that I could factor out. And when I do that, I'm left with a cosine squared plus a sine squared, which simplifies to 1. And so really here I just have sine phi, cosine phi. Now I need to go ahead and actually find the norm of this cross product. So if I set this up, I can see here that what I'm going to end up with is a sine to the 4th phi cosine squared theta plus sine to the 4th phi sine squared theta plus a sine squared phi cosine squared phi. All right, now actually there's a lot that can be done with this as well. Again, notice in the first two terms, I have a sine to the 4th of phi. And when I factor that out, what's left over, the cosine squared plus sine squared, is just going to turn into 1. So this leaves me here with a sine to the 4th phi plus a sine squared of phi cosine squared of phi. However, when I look at these two terms, there's a sine squared of phi that I can factor out from both of them. And when I do that, what I'm going to be left with again is another sine squared plus a cosine squared. And so ultimately here, I'm just going to be left with a sine squared of phi. Of course, when I square root that, I should end up with the absolute value of the sine of phi. But if I go back and look at the bounds that are on phi, phi goes from 0 to pi. On that range, the sign is always positive, and so those absolute value bars aren't actually really doing anything, and so I just end up with sine of phi. Okay, that is a lot of calculations just now to get down to my surface integral. So my surface integral here of z squared should now be able to be rewritten. This is going to be a double integral, and my z should be able to be updated here. Remember here that z was the same thing as a cosine of v, so I can write that here as cosine of v all being squared. Then I can go ahead and write my sine of phi, right, as that's what I've simplified down to. And then I'm going to go ahead and write out my differentials. I'm going to choose to do d phi d theta. Phi went from 0 to pi, and theta went from 0 to 2 pi. So boom, here I am. I have my integral fully set up. Now again, this is a fairly simple integral to Sorry, I just realized here this should be cosine of theta. I don't know why I wrote cosine of v. My apologies. But overall, this integral here should be actually really, really easy to evaluate because it's just a simple double integral. I'm not going to go through it here. I think it does require a u sub. Full details are in the notes in Blackboard. I think ultimately, if you computed this all the way out, you end up with a final value of 4 pi over 3. So hopefully, again, you're feeling a little bit more comfortable here with the process. Usually this step down here doesn't take too terribly long, and most of the effort goes into finding the parameterization and then actually setting up that cross product and computing that norm.